Hi, we will be presenting to you our machine learning project. We are from Lab P2 Group 11, which consists of myself, Azim, Dani, Edson, and Samuel. So we'll be covering to you the project details, the data pre-processing, the model training, the model testing, and lastly, the improvements. So the problem is our math tutorials are submitted through Gradescope is not being graded. This is due to the student assistant or professor not grading our work. This therefore hinders our learning process. So the solution we have come up with is an automatic grading system for Gradescope, which consists of the answer detection, the digit extraction, and the digit classification. So it would automatically identify the location of handwritten uh, answers on the paper, the digits being detected with precision. The digits is consists of 0 to 9, and also decimals if present. Next, I'll be handing over to Edson.
Okay, thank you, Amiro. I'm Edson, and I'll be sharing about our data collection and pre-processing process. We'll be using the NIST dataset, which is a well-known collection of handwritten digits commonly used for training image processing in systems. So this dataset consists of 60,000 training and 10,000 testing images, all of which are grayscale and measured by 28 by 28 pixels. Initially, the pixel values are in the range of 0 to 255. So the standard deviation of the pixel values is 78.6, which indicates high variability in pixel intensities. This variability is important for training deep learning models as it introduces diverse input patterns that improve the model abilities to generalize. So here's an example of what the data looks like before any pre-processing. Before we train our models, we'll normalize the pixel values, scanning them from the original image of 0 to 255 to a range of 0 to 1. This normalization ensures that all inputs have the same scale, which reduces the computational complexity and helps with faster convergence during training. Additionally, we'll flatten the images. Since the original format is 2D, we'll reshape it into 1D vector, resulting in 786 pixels per image. This step is essential for classical machine learning models. So, we have trained a total of 5 models. As you can see in the table, the CNN model outperforms the other across all metrics. Given its superior performance, we'll be using the CNN model for input prediction. Next, I'll walk you through how we train the CNN model. To begin training our CNN model, we'll first implement multi-channel inputs by adding a single channel to reshape the grayscale image into 28 by 28 by 1 format. On the left, you can see the summary of our CNN model. We use convolutional layers to extract important features such as edges, textures, and patterns. The value activation introduces non-linearity, which is crucial for learning complex patterns and helps prevent the vanishing gradient problem, which speeds up training. The HE uniform kernel initializer ensures proper weight initialization, while the max pooling reduces the spatial dimensions by preventing overfitting by removing unnecessary details. Next, I'll apply a few callbacks to save the best model parameters during training. So early stopping halts training if validation loss doesn't improve for 5 epochs. The reduced LR on plateau reduces the learning rate by half, and model checkpoint save the best model based on the validation loss. As shown in the confusion matrix, the model is performing very well and training effectively. So now I'll be passing my time to Dani.
Hi. So for our classical model training, we utilize grid search CV to select our optimal hyperparameters for our models. Specifically, we focus on 4 classical machine learning models covered in a module: k-nearest neighbors, random forest, logistic regressions, and support vector machines. Grid search CV systematically tests all possible combinations of hyperparameters provided in a predefined grid and identifies the best configuration. Given the computational intensity using grid search CV on our dataset, which contains 60,000 samples, we perform hyperparameter tuning on a subset of only 5,000 data points. After identifying the best parameter for each model, we then train them on the entire training dataset to maximize their performance. To further optimize training time, we experimented with cross-validation settings of either 3-fold or 5-fold validations. The parameter grids and the best parameters for each model are detailed in this slide. Now, Azim will explain how we detect decimals and segment digits.
Thank you, Dani. So for the actual usage of our algorithm, we first have to pre-process the input image. Our input image is an example of which is in the middle of the slide there. Now, in order to identify the answer out of the whole image here, we use OpenCV's contours to detect the box containing it. Then we split up the multi-digit into individual digits again using contours, and finally pass each digit into the models to predict. For answers with decimal points, we have our own detection. The central idea is this. If the bounding box of a segmented digit is small, square, and low, consider it to be a decimal point. In order to check if it is small, we use area, whether it is square, aspect ratio, and finally, whether its position is low enough, we check its midpoint. First, area. As decimal points are usually very small in area compared to the rest of the digits. Secondly, aspect ratio. As prominently for the digit 1, it can have a tall height but very thin width, causing it to have a small area and thus throwing off the detection. Thirdly, their midpoint is compared against the average midpoint of all the digits to determine whether they are low enough to be considered as a decimal point. With these three checks combined, identifying decimal points is achieved reliably and without the need to train the model explicitly for decimal points. Now, Samuel will be talking about further refining the target image to retrieve only the important data. Thank you.
Thank you, Azim. Okay, so in our earlier versions of model testing, we encountered significant issues caused by the noise from lined foolscap paper, as seen on the image on the top left. So these imperfections from the drawn boxes factors to the misidentification of digits and decimals, making the model's performance much less reliable. So what's the solution? After extensive testing with various noise reduction techniques, I found that the optimal solution was to process the crop images using three key techniques: Gaussian blur, thresholding, and morphological operations. By applying these methods, we were able to smooth out the noise, convert the image to binary format, and remove the isolated pixels, resulting in an improvement in the quality of the images fed into the model. So despite these improvements, there are still some key limitations that need to be addressed. After testing on various handwritten math equations, I identified the following limitations. Firstly, adequate spacing between digits is crucial for accurate segmentation. When digits are too close together, the model may struggle to correctly identify individual numbers. Secondly, negative signs were frequently removed. This often occurred because the negative sign was too small or thin, causing it to be filtered out along with the background noise. Thirdly, bounding boxes are used to crop the image around the digits, but imperfect cropping can result in digits being cut off, such as the number 3 in the image on the bottom left. Lastly, as with all machine learning models, false predictions remain a challenge. These errors are typically due to subtle variations in the handwriting or the presence of residual noise. I'll now pass my time on to Amir.
Thank you. Thank you, Samuel. Now I'll be talking to you about improvements. This is the what use or what could have been, but due to the performance, it wasn't implemented. So was based on when the digit recognition model was already working. I thought of alphabet recognition and math symbol recognition. So as you can see, based on the training model, it achieved 86% accuracy and it manages to predict one-for-one label. So the program works when integrated with our digit is when it loops through, first it loops through the digit recognition model. Based on the confidence score, if it's lower than 0.4, then the alphabet model will be used to predict. As you can see, the real image is 5L. However, it predicted 5 and 6, which is B, so 5B. Therefore, it wasn't implemented in the end. So for my math symbol recognition, the data set wasn't good enough. So the data set I used was generated synthetically with parameters, as you can see below. Training accuracy achieved for this model was 50%. For the real images, I use a plus and and a minus. So the addition it manages to predict. However, for the subtraction, it did not. So therefore, these two models wasn't integrated. With that, we have come to the end of our presentation. Thank you.